Hello everyone, and welcome back to Lecture 12. What we'll be doing in this last video is we'll finally be talking directly about soundness and completeness. In particular, we're going to sketch a proof for the soundness of our system, our TFL system, and then we'll talk through an algorithmic way of showing the completeness of our TFL logical system. So let's get started. So we can say that a formal proof system is sound relative to a particular semantics if and only if there's some formal proof of C from some assumptions among gamma, then gamma entails C, given the semantics. So in other words, right, a natural deduction system in this case is going to be sound relative to a semantic approach if and only if, right, if we can construct a proof, then the tautological entailment also holds. So what we're going to try and show is this soundness theorem. For any sentences we might take on the left-hand side of our single turnstile or our double turnstile and a single sentence C to the right. If the provability claim holds, then so does the entailment. And the proof method for this is actually fairly straightforward. What we'll do is we check each natural deduction rule that we have for TFL, and we'll show that no application of any rule delivers bad results. That is, we'll show that, hey, this side's cool, and this side's also cool. We can introduce a notion here. We can say that a line of a proof is solid if and only if the assumptions the line depends on tautologically entail whatever's on that line itself. And we can then, using this idea, show lemma 5.2 that every line of every TFL proof is solid. Again, where solid is defined in this way. So the proof here is fairly straightforward, and it's going to hinge on using lemma 5.2. So here's the proof in a sketch. Every line of a TFL proof is obtained by applying some rule. Either it's an assumption or it's applied by a rule. So let's say that a rule of inference is rule sound, if and only if, for all TFL proofs, if we obtain a line of a TFL proof by applying that rule, and every earlier line in the proof is solid, then the new line's solid too. If every rule is rule sound, then the proof system is going to be sound. So in effect, right, what we're saying is, right, if, right, whenever you're using a particular rule, the thing that produced is solid, then it's going to be solid too, provided that a rule, whatever rule we've used, is rule sound. So all we have to do now is kind of do the soundness. And really the sketch here is going to lean into a proof for 5.2. So assuming every rule is rule sound, take any line n of any TFL proof. The sentence written on line n must be obtained using some inference rule which is rule sound. By definition, if every earlier line is solid, then n's going to be solid. So basically by strong induction on length, which you'll remember from the previous lecture, every line of every TFL proof is solid. In effect, what we're doing here is a condensed version of a strong induction. Right? In this case, a strong induction on length of sentences in our TFL proof. The trick here really is proving 5.2. Again, we can get this via this kind of thing. Now, the only real thing left in order to prove soundness is to show that every rule is rule sound. And to do this, it's actually fairly straightforward, but it's tedious. So I'm not going to go through them here. I think Tim does a really nice job of doing this in the meta theory book. Basically, the real easy way to think about what we do here is, right, just think using our, again, sexy swash font letters, we can construct a proof using every particular rule. We can then construct a corresponding, say, truth table or semantic approach to show that we're going to have a tautological entailment going across. We do this for every one of the rules, show that every rule is sound, and we're good to go. So that's it for soundness. It's actually fairly straightforward. And again, what does soundness show? Soundness shows us, right, that if provability holds, then tautological entailment holds. So that's kind of nice, right? Our proof theory is going to be sound relative to our semantic approach. That's nice. But of course, that's only half of what we want to do. So we can conclude that our TFL natural deduction system is sound relative to our semantic approach. But we want to go the other way. The other way is to show completeness. And we can say that a formal proof system is complete relative to a given semantics if and only if delta entails C, then there's a formal proof of C from the assumptions among our collection of sentences. In other words, right, for any sentences, right, if tautological entailment holds, provability does too. This is actually going to be slightly harder. So soundness is fairly straightforward. We can basically work through each rule, show that the rules work, and if the rules work, then our proof system is guaranteed to be sound. Completeness, a little more difficult. What we're going to do for the completeness proof is we're going to lean into lemma 6.2. 6.2 says for any sentences, any collection of sentences, if they don't prove a contradiction, then there's going to be some valuation that makes all the sentences true. That is, if our sentences aren't jointly contrary, then they're going to be jointly consistent. We're going to use So our proof for completeness is going to use lemma 6.2. It goes like this. First, we're going to suppose that our collection of sentences does not, like there's no proof, taking these as assumptions, that ends in C. Right? Okay, so we're going to run with this assumption. Now, if there was a proof of negation from our sentences and not C, then we could use negation introduction and double negation to obtain a proof of C from our initial sentences. Again, this is basically what we do when we prove something indirectly. But of course, if we could do that, then we'd have contradicted our initial supposition. There would be a proof that starts with our sentences and derives C. So, what we can conclude from this is that our sentences and not C don't prove a contradiction. That is, these sentences are not jointly contrary. Now, by lemma 6.2, which again we had on the previous slide, we can go back. And lemma 6.2 says for any sentences, right, if they don't prove a contradiction, if they're not jointly contrary, then there's some valuation that makes them all true. So by lemma 6.2, there must be some valuation that makes our collection of sentences and not C true. By definition, this then means that our sentences do not tautologically entail not C. Okay, so far so good. Now, what do we get? Well, remember our initial supposition. So our initial supposition was that our sentences, you can't prove C. So we can now effectively do something like conditional, right, introduction. We can say if from our sentences you can't construct a proof for C, then there's not going to be any kind of tautological entailment from these sentences to not C. Now, by contraposition, where effectively we just now flip around the negations, this entails that if tautological entailment holds, then the provability holds. Again, the thought here, right, is you can see this as if not B, then not A. This is going to then be equivalent to if A, then B. So that's kind of cool, right? We basically can show that this conditional has to hold, and if this conditional holds, then the opposite way around must also hold. Really, the whole trick here is to prove lemma 6.2. And to do this, we can actually construct a really cool little algorithm, and the algorithm's going to do the work for us. So the algorithm we're going to call simple search algorithm. And what it does is it determines for any arbitrary sentences whether or not these sentences are jointly contrary. So if our sentences are jointly contrary, then the algorithm outputs a TFL proof, which starts with them as assumptions and terminates in a contradiction. If they're not, then what it's going to do is actually yield a valuation that makes all the sentences true. So in that way, the output of the algorithm is either going to be a proof that they're jointly contrary, or a valuation to show that they're jointly consistent. Basically, the algorithm looks for situations where it can apply this kind of negation introduction rule, or as we can also call it, negation elimination. Okay. And again, what we're going to try and do here is it's going to be in the main proof. We're not going to be in the subproof. So it goes like this. Right? We're going to write out the sentences and assumptions, and we're going to put them in conjunctive normal form. So you remember that from earlier. And this is basically because it's going to allow our algorithm to do some separation and make everything work a little bit smoother. It's not strictly necessary, but it makes the algorithm work easier. And then the algorithm's basic strategy is to use conjunction elimination until you've gotten down just to parts. Then we're going to introduce assumptions to break the disjunctions we have. We're going to try and use negation elimination rule within the subproof to derive contradictions. And what we want to do is derive contradictions using disjunction elimination. So it's helpful to go through these step by step. So again, our first move, we're going to have our sentences, our sentences that we want to evaluate, and we're going to put them all in conjunctive normal form. Now, once we have them in conjunctive normal form, the algorithm's first step is to apply conjunction elimination until no further applications yield a sentence not already obtained. Basically, break all the conjunctions as far down as we can. So the output is going to be either atoms, negations of atoms, or disjunctions. So that's going to be, and again, it's going to have to be that because our sentences are in conjunctive normal form. So we break it down until we've got the parts as far down as we can go. Then what we'll have is we expand disjunctions. The idea here is we basically write them out so that we're trying to set up for disjunction elimination. So for example, what we've got here, right, we've got some sentences. We're going to write out A or B and expand them out, put them in subproofs. And the aim is, again, to try and do disjunction elimination eventually. And inside these, we're also going to expand our other disjunction, and we have to do them in both. So the result that we get here is a kind of proof skeleton. It has gaps inside these subproofs. And the lines are all atomic sentences or negations of atoms. Again, why is that? Because we're using conjunctive normal form. So we first move, snap all the conjunctions to get down just to atoms or disjunctions. Second move, expand disjunctions. That is, set up for disjunction elimination. Now, importantly, what you need to do is expand all the disjunctions. Why are we doing this? Now, the aim will then be to apply negation elimination whenever possible. That is, try and generate contradictions inside the subproofs. And hopefully what we'll be able to do is produce contradictions inside every subproof. Because what we can then do is use disjunction elimination to derive our contradiction onto the main proof line. So for example, right, we've expanded in the previous slide. We then are in a position where we can use, we can derive a contradiction in this subproof and a contradiction in this subproof, and then get a contradiction using disjunction elimination. We can do the same thing over here, and then that means we've got contradictions in both of our disjuncts, so we can then derive the contradiction on our proof line using disjunction elimination. So again, the aim is to try and generate contradictions inside the subproofs using disjunction elimination to pull that contradiction back to the main proof line. If we can do it, then it's guaranteed that the assumptions are jointly contrary. It's very cool. Again, it's a mechanical process here to tell you whether the sentences are jointly contrary. Now, of course, this will work if they are contrary. What happens if they're not? Well, if they're not jointly contrary, our algorithm's going to follow the same steps. Again, first move, we have our sentences in conjunctive normal form. So our first move will be to apply conjunction elimination until we're down to atoms or just disjunctions. Okay. We're then going to expand the disjunctions, again, manipulating it to try and set up for disjunction elimination. We're then going to apply negation elimination whenever possible to generate whatever contradictions we have. But take the cases where there are no contradictions. So for example, here or here. What's striking is in these gaps, we still have just the proof skeleton. But the proof skeleton, in fact, specifies a valuation. So for example, look at this one. We have a gap. We can't use negation introduction to derive a contradiction. So now what we know is that if we make C false, A true, and B true, all of our initial sentences are going to be true. So what we can do is use the gaps to read back off some valuation that makes our sentences true. So it's really cool. Our proof skeleton shows us a valuation that indicates our initial sentences are jointly consistent. Meanwhile, if it completes and we get the contradiction back on the proof line, our algorithm tells us the sentences we started with are jointly contrary. So that's really nice. This algorithm is a mechanical way to evaluate whether some sentences are jointly contrary. If they are, it will generate the proof. If they're not, then it's going to generate a valuation. So just to kind of sketch the algorithm again, so given any sentences, we can start a TFL proof using these sentences as assumptions. Then for each sentence amongst our collection, we apply the algorithm which finds a conjunctive normal form sentence that's tautologically equivalent to it. We then apply conjunction elimination until no further applications yield a sentence we don't already have. We then expand each disjunction in turn inside our various expanded disjunctions with the aim of eventually trying for disjunction elimination. You then check each open line to see whether negation elimination can be applied. If it is, do so. You then check all open lines to see whether disjunction elimination can be applied. If so, do so. Hopefully what you'll then get is a proof, a complete proof, that shows you how to generate all the contradictions, shows you how to get the contradictions out using disjunction elimination until it's back completely on the whole proof line. If it is, you know that your initial sentences are jointly contrary. And the final step of the algorithm is, of course, just output the proof. Or, if they're not jointly contrary, the proof skeleton, which we can then read off a valuation that makes our initial sentences true. So this is really neat. Again, it's a kind of mechanical way to think about whether sentences are jointly contrary or jointly consistent. And the big role that this plays, just to go back, is that this then gives us a way to support lemma 6.2, which we wanted because lemma 6.2 was our key step in our proof for completeness. So we can use the simple search algorithm to provide us with a way to justify lemma 6.2. And using lemma 6.2, we can then prove the completeness of our proof system. So here's how we get to 6.2. We can get lemma 6.5. Right? If simple search outputs a proof skeleton whose last line is a contradiction, then our sentences are going to be jointly contrary. The proof here is actually quite simple, right? Simple search only applies the rule of TFL proof system. So if the last line's a contradiction and we didn't have any other assumptions, then the rules are going to be able to take us from our initial assumptions to a contradiction, which is the definition of being jointly contrary. The flip to it, 6.6, is that if it doesn't output a proof skeleton whose last line's a contradiction, then at least one open line, and there's at least one open line in the skeleton. Every open line yields a valuation that makes our initial sentences true, and our initial sentences aren't jointly contrary. Now this one we can just derive directly from the definition. This one we can just simply read backwards. And this is going to be simply by definition, because the way the simple search algorithm works, the only way you're going to get an open line is if there was no way for it to complete it. So that's kind of neat. And then finally, this can give us theorem 6.7. Right? So given any sentences, right, if they derive a contradiction, simple search yields a TFL proof that begins with our assumptions and results in a contradiction. And if they don't, then the simple search algorithm demonstrates that they're not jointly contrary, yielding a valuation that makes them all true. And we can basically prove this just simply using the two things we sketched just a second ago. By 6.6, right, then we know that it's going to be able to derive this kind of contradiction. Flip, right, if they're not jointly contrary, then it's going to output a valuation that makes all of our sentences true. So it's kind of cool. Again, simple search is guaranteed to get us to where we want to be. Kind of nice. And the big shot then is this vindicates 6.2, which was the key step we needed for our completeness proof. So the upshot then is that our TFL semantics are complete relative to our TFL natural deduction system. That is, again, when we combined the results we had earlier, we're going to get this relationship that we wanted. Whenever provability holds, so does tautological entailment. And that's awesome. So again, this was kind of complex, actually very complex, and there were a lot of moving parts. The upshot is incredibly powerful because what it again means is that our natural deduction system and the semantic approach we have with truth tables go hand in hand. You can use either one, they're never going to lead you astray. So that's the kind of upshot metalogical results. Now we went quite quickly, and I realize a lot of it's going to be possibly over people's heads or maybe didn't make sense. It might be helpful to go back through the Metalogic book. I did things slightly differently than Tim does in the book for some of these, mostly for ease of presentation and for succinctness. Happy to talk a little bit about this stuff. I think, yeah, it's very cool. So, again, the big upshot is our soundness, our natural deduction system is both sound and complete relative to our TFL semantic system. So we can use whatever tools we have in our toolkit to approach questions about validity, joint completeness, or joint consistency, or joint contrariety, showing things are tautologies or contradictions, showing things are equivalent or not. And that's very cool. Now, this is it really for us talking about logic. It's kind of a fun way to end. What we're going to do in the penultimate lecture is we're going to talk about set theory. So set theory is the foundation of much of modern mathematics. It's very useful for you to know. What I'm going to do with regards to the set theory lecture is, again, it's mostly going to be me talking at you, giving you some interesting stuff. There will be very few things in it that we will actually talk about with regards to the exam. I'll specify exactly what it is. Again, I'll make an announcement about it and get everything clear. Expect videos shortly too about the nature of the exam. I'll give you some details on that. So thank you guys very much for coming. I hope you've enjoyed this lecture, and I look forward to talking with you about both metalogic and set theory in the future. Bye guys.